this Thursday problem here. In part B, I don't think you answered the part of the question that was asking about the difference in concentration between the front of the bacterium, the front of the cell, and the back of the cell, where concentration is 1 at this part of the tube, and this is x equals 100. Excuse me. Concentration is 0 at this end of the tube, and x equals 0 here. At the back of the cell, assuming the cell is facing forward, facing the high concentration, the back of the cell, x equals 45. At the front of the cell, x equals 55. So I'm going to get a C of x, an equation for C of x, and then to get the difference in concentration, I'm going to do C of 55 minus C of 45. And that'll give me the difference. Now, I'm using chapter 4, figure 411b, B as in Bravo, to make this equation, and I've got x is 0 here, and I've got x is 100 over here, and I've got C is on the y-axis, x is on the x-axis, so this is C equals 0 right here, and this is C equals 1 right here. So at C equals 1, x equals 100, so that's this point right here. At C equals 0, x equals 0, that's this point right here. This is a steady state, so that means it's a straight line relationship, and this is a line with the equation y equals mx plus b. The m is the slope, change in y over change in x, and change in y is 1. Change in x is 100, right? So the equation of this line is C of x equals m, so y equals m, x plus b, and b is 0, and y-intercept is 0 here. Now I have my equation for the C of x, so I'm going to substitute in C of 55, so we've got 55 over 100, and substitute in 45, so 45 over 100, and that gives me 10 over 100, and that's 0.1 in whatever concentration units they have. That's the difference in concentration between the front of the cell and the back of the cell. Now, I wanted to say a few things about part C. I agree with you that this should be a 1D problem, because we're not interested in any other position except for the position that is 10 microns away from the front of the cell, you know. So I agree with that, and I want to redo the calculation to show you that the using your method, the seconds does end up becoming a reasonable number rather than the huge number that you wrote down. I think you just had yeah, I think it was you were messing with the units or something. So let me do that over here. So x squared over 2d is roughly equal to the time that it takes, and the x is in this case 10 microns, which is 1 times 10 to the minus 5 meters. So we're going to square that and put that over 2d. d, in this case, they asked for it to be 10 to the minus 10. Now the units for the d were meters squared per second, and this is meters squared, so meters squared is going to cancel. This is per second is going to go up here, so it's going to end up being in seconds, which is what we want. Time is in seconds. So when you the meters squared cancel, but this squared is also for this guy, and when you square an exponent, you multiply them. So if you do this on your calculator will agree that this is 1 times 10 to the minus 10th up here, over 2 10 to the minus 10th. So these 10 to the minus 10ths cancel. So this is going to be 0.5 seconds, right? Now, I don't agree with your work for part D, because you said it was a 2D problem, but I believe that it is the same as part at C. The same argument by which you decided that this should be a 1D problem, one-dimensional problem, it is the same argument by which you should decide that D should be a one-dimensional problem. But the only difference is that they gave you a hint. They said assume that the cell is like a globe, and that you're going to travel the surface of the globe. You do not travel through the globe to travel the surface of a globe. You have to travel on the curved surface, and the curved surface, any path on the curved surface is really a circle. It is a circle that is a kind of a slice of the globe. So this circle from the front to the back end of the cell ends up being a semicircle. We just want the semicircle. And that semicircle length is half of the circumference of the globe. If we slice a globe, we're going to see a circle as the rim. And half of that circle is the path that we need the membrane protein to take. And so the radius of this globe is half of the diameter, which was 10 microns. So the radius is 5 microns. And now this is going to make kind of a big difference, because look at this. This is 10 to the minus 6, whereas before it was 10 to the minus 5. Right? So let's see what happens here. Right? So the x squared over, I'm going to do this as a one-dimensional problem, and the x is going to be equal to 1/2 of the circumference, because the path is a semicircle. So that's going to be 3. I'm going to just say that pi is 3. 3 times r, which is that. So it's going to be 15 times 10 to the minus 6. It's going to be 15 times 10 to the minus 6. I'm going to square that, divided by 2d. d, in this case, they said it's 10 to the minus 11. All right? And this is still meters, and this is still meters squared over seconds. All right, give myself some room over here. Well, actually, I can just roll the page down. Okay, so this is supposed to equal to t. Supposed to be equal to t. So I'm going to do this on the calculator so I don't mess it up. Okay, so 15 times 10 to the negative 6th squared divided by 2 divided by 10 to the minus 11 is equal to 11. So it takes about, well, to one significant figure, so this is about 11 seconds, but to one significant figure, that's about 10 seconds. All right? So that 10 seconds, that's a lot more than half of a second. That's how many times more? 50 times more? No, 20 times more? Yeah, that's 20 times more. So that is 20 times longer. So it takes a membrane protein 20 times longer to get from one end of the cell to the other end of the cell than it does for a cytoplasm protein to get from one end of the cell to the other end of the cell. It takes 20 times longer, at least 20 times longer, maybe more. So I think that's a pretty good argument for the sensors to be membrane proteins rather than cytoplasm proteins. That's it. Now, just in case you wanted to discuss my 1D argument here a little more, let me do that. So, if you didn't want to discuss that, feel free to just stop the video and just forget about it. But, the 1D case is like this. The 2D case, of course, what you did for part D is like this. The 3D case is like this. So you could see that the time is shorter as we go along. So the time is shorter for the 3D case because there's a large denominator. Time is a little longer for the 2D case, and then the time is longest for the 1D case because the denominator is the smallest. So what does that mean? I think that means that with the 1D case, we're interested in starting here and ending here. But in the 2D case, we're interested in starting here and ending anywhere on this circle. In the 3D case, we're interested in starting here and ending anywhere along this sphere. So there are more possible destinations here. That's why it takes a shorter time. And there's a medium number of destinations here. That's why it takes a medium time. But there's only one destination here. And I think that's why it takes a longer time.